then we basically move to the a general setting that we can suppose you have more actions, right? And then or general sum setting rather than zero sum. You can't solving by linear programming, but you can solve by a so-called linear complementary program. So here is the observation: is that as I said, let's consider that we have mixed Nash equilibrium, X star and Y star, and this mixed strategy is there's no pure strategy. In other words, that X I star for any of this pure strategy, the probability of choosing them would be larger than zero. So in other words, that we don't have any pure strategy, we're not going to select. There's a certain probability you're going to select that. So equally for J as well. So all pure strategy are used with positive probability. So let's denote AI, denote the row of the payoff matrix A, and the BJ denotes the column of the payoff matrix B. Okay, so if we assume every pure strategy is played with positive probability, this would be the exactly same as last time when we're talking about a simple solution for solving the Nash equilibrium. I will make no difference. I will choosing my probability in such a way I will make no difference for other users to change their policy, right? Therefore, these they also do using the mixed strategy rather than pure strategy. So in other words, in the Nash equilibrium, when I choosing my policy Y, right, and this AI basically is the A1 is basically the is a row of the payoff of matrix A, and then when you multiply with Y star is basically the payoff for player one. They choosing this first pure strategy, right? This is the expected payoff for them. So they will equal to the rest of the payoff for choosing other pure strategy. It's simply because I would choose Y in such a way that they will make no difference between all this strategy. Equally for player two as well, because in player two is that the player one gonna choosing their strategy X star in such a way they will make no difference between their pure strategy. Okay, all this need to have assumption that assume every pure strategy is played with positive probability. So that gives us a very interesting characteristics of Nash equilibrium is that any pure strategy that is in the support of the Nash equilibrium. When I say support, basically say that pure strategy is actually played with positive probability. Now, in other words, that the value of that, the Y's in that direction is larger than, 0. So as the assumption that every strategy is played with positive is quite restricted, because not necessarily, right? The games that you have the so-called totally mixed Nash equilibrium. In other words, some of the pure strategies are not really useful, right? They probably the payoff from that particular action is really small, that you don't really want to pay it, right? You don't need to want to play it at all. So for that kind of so this we need to have better formulation for that characteristic. So and basically we will say that suppose you got a mixed strategy profile X star and Y star, right? It's just a Nash equilibrium, and we could introduce the concept of a support. Okay, so what the support means is that support is a subset of this pure strategy P. You can think about a subset of these pure actions where these players are played their probability of playing it would be larger than 0 in Nash equilibrium. Okay, and so equally S1, and here the bar, lowercase bar, I don't know how to call it, is subset of this entire action that player 1 gonna have. So equally they have this the S underlying 2 is a subset of this from player 2's action set, and it is a support for a player 2. So you could, if you define that, basically say, okay, they would have same value, okay, for I, for this pure strategy index I, if they are in the support set. And if it's not in the support set, and I won't play, remember, I won't play that kind of action. Therefore, the value would be sort of smaller than that, right? Smaller than that. And it's quite obvious. If you're larger than that, obviously you're gonna play that particular action. So you can also apply to the opponent as well. The other user, they follow the same thing. So the definition of that, if you're looking at this, is basically say x star I equal to 0, that is not in the support of that, and equally yj is equal to 0 is not in the support of that. So the uv basically is a value of the value and the payoff, expected payoff in the Nash equilibrium. So think about this is that as long as you would able to find this support sets, okay, then you would able to write it down this sort of because this in the support set, the probability of choosing a larger than 0, and these expected value for that pure strategy would be equal to all the other pure strategy in the set, and therefore because use that you can actually find Nash equilibrium, quite straightforward. So really the competition is try to really find all possible supports, right? And the competitionally is extremely difficult, and actually people in game theory really study this computational complexity is really focused on this the algorithm to find a support set, which we'll talk about in a minute. Then for this general sum, okay, for this general sum rather than zero sum, and because we lose a connection between max and minimization, right? Because we in this because in the zero sum is complete opposite the player 1 and player 2. Therefore, in fact, it's a single agent problem rather than multi-agent problem. And because you know this agent A, you immediately know the reward for agent 2. Therefore, it's really they are absolutely correlated, isn't it? So in that case, you could convert that into a LP problem. However, in this case, it's become bilinear. Okay, so you can't just say I would only consider player 1 and find a solution, and player would be happy as well. So you have to combine them together. Therefore, create this so-called bilinear programming problem. So to think about this is that this is sort of looking at this is that I got this in P and Q. So P and Q is basically upper bound. Think about this, they are upper bound of this sort of for each of the agent, right? The XY is basically will become a vector of expected payoff for, let's say, agent 1, agent X. And the B transform X is expected payoff for agent 2, agent Y. And so we want them to be upper bounded by an P and Q. Basically, this is the best reward they can actually achieve. And they only achieve, let's say, in the Nash equilibrium. And obviously, we want to make sure that we want to make sure that this is sort of final achieved ones, because it's already multiplied with the policy from the both x and y. So this is expected payoff for agent x. This is the expected payoff for agent y. We want to basically to sort of maximize the difference between them, right? We want to make sure to maximize difference between them. And so by doing this, we can formulate the Nash equilibrium. The solution of the xy is basically the Nash equilibrium for that. So think about this. In fact, you could write it down as a linear complementary problem. So the difference between them is that in standard optimization, because in the end, what you want is that it's really nothing. It's really 1, 2, then equal to 0, isn't it? You want to basically, this is the one that I'm going to achieve when this guy equal to this and this guy equal to that. And you want to make it sort of achieve on, because this is sort of a upper bound. You can think about this upper bound. This is sort of upper bound as well. So so this x transform y, x transform ay would always lower than p, and this would always lower than the q. But of course, that you want to sort of maximize it. Therefore, the best achievable one is basically 0. So in fact, you not really do the optimizing at all. You just want to make them equal. So that's why you can actually create as a linear complementary problem. So there's a linear complementary problem. There's no maximization or minimization. Is a feasibility program. So when I say feasibility program, is that they have a bunch of the constraints, and you want to find a feasible set to fulfill those constraints, and those feasible sets that fulfill that constraints, in fact, is the Nash equilibrium. So and this is sort of LCP problem, and it can be used to solve this Nash equilibrium. So let's just have a look of this. What we actually add, if you're looking at this, is we got this still. Think about this x1j. So 1 and 2 is basically the player 1, player 2. J is the index for the Pew strategy for agent 1, and K is the Pew strategy index of agent 2. And we obviously wanted the Pew strategy equal larger, because their probability want to equal larger than 0. Then we also introduce the slack variable, as we explained before, right? If we want the slack variable be larger or equal to 0. This is an additional sort of a constraint we adding. This is quite similar to this strong duality condition that we specify. We need one of them to be 0, as we discussed last time. If the slack variable is 0, and that means that we allow that Pew strategy, the opponent Pew strategy, to be played equally. If this is not a variable, if that slack variable is non-zero, and that means that that particular Pew strategy, the expected payoff of that, haven't really achieved the optimal down they can actually achieve. Therefore, the probability being playing it, this aspect and the probability being playing it would be 0. Otherwise, it's not equal. So that kind of additional constraint to it. So this formulation basically is quite similar to the LP formulation of slack variable, but without this objective. And the first constraint is the same as that in our LP formulation with the slack variable, as I mentioned. However, we also include the second constraint, which constraint player 1's actions in the same way. So we got this all these actions for player 1, all these actions for player 2. They need to fulfill that kind of relationship, as I said. If usually in a support set, the probability being 0, right? If you're in the support set, the probability of select that action is larger than 0, then that with respect the slack variable would be 0. Okay, if this slack variable is 0, and then means that you have certain probability of choosing that, then that probability for the action would be larger than 0. So that's basically is a formulation to extract that relationship as we mentioned in the Nash equilibrium. And so these are the ones that standard sort of constraint make sure that there are probabilities. But here is a constraint for the set variable has to be larger or equal to 0. So that's the So the problem with this constraint we have described so far is that we got this upper bound U1 star and U2 star, and so if you just looking at this and without this sort of additional constraint we were reinforced, like this constraint we enforced, the solution wouldn't be unique. There will be take unbounded large, because you can, when you take this quite large value, you can always make this large value as another solution. Therefore, you will have a sort of a unbounded large value for that. So, but adding this wouldn't allow that happen anymore, and actually reinforce that kind of relationship. That's why we call complementary condition is this nonlinear constraint. So if when we adding this, that we no longer as linear program anymore, but rather is a linear complementary problem, because they are complementary to each other. So I'm going to repeat what I said again, and here's actually already written here as well. So for you to really understand this, is that so when the action is played by a given player, okay, if that action is played by the player, let's say suppose this J action from player 1 being played by a given player with positive probability, and this one would be larger than 0. If that's the case, then in order to make this constraint hold, then therefore the slack variable R1J is actually something here. So maybe we can not using this. We use this example. So suppose a player 2's action K is played with positive probability, then their corresponding slack variable, which is R2K, would be 0, right? Because if this one is larger than 0, then this constraint holds, then this R2K has to be 0. Then this has to be is 0. Basically, what this means is that given this player 2, okay, this player 2, their action their action K, the expected, this is basically the expected payoff for that if you're taking that particular action, K, right? This is AS1J is this mixed strategy from this opponent 1. So basically this indicates the expected payoff for player 2 if they're taking action A, and that one, because the slack variable has to be 0, that means that one would be the support of the Nash equilibrium. Therefore, they achieve the maximum value. Of that utility of the payoff. So what this means. So each slack variable can be reviewed as a player's incentive to deviate from the corresponding actions, right? When this action is not equal to 0, let's say not equal to 0, larger than 0, and then this one has to be 0. Then, in other words, I deviate from my Nash equilibrium because that particular action has to be 0. Sorry, the probability of playing that action has to be 0. And therefore, I don't play that particular action. So therefore, this complementary condition recaptures the fact that in equilibrium, all the strategies that are played with positive probability must have the same expected payoff, right? As we sort of expand quite a number of time already. While all the strategies that lead to the lower expected payoff are not played. So this is very important characteristic of Nash equilibrium, mixed Nash equilibrium. Taking all of these constraints together, so each player play a best response to the other player's mixed strategy, therefore fulfill the definition of the Nash equilibrium, right? Because they are in the support, therefore the probability rather than, and they will play on that particular action. Therefore, it's the best response. So this is really consistent with the theory of linear programming, right? In the linear programming, we have this similar relationship. If you're looking at similar relationship as we will specify there.